So let's go through our nested loop join algorithms. So for the simplest case, suppose we have a bunch of pages from the relation R and a number of pages in the relation S. In the simple nested loops join algorithm, we're going to iterate through every single record in R. And then for every single record of R, we're going to pair that up with every single record in S. And then we are going to check against the theta function by passing it both of the tuples. Now, the theta function basically acts as the join predicate, and it's going to return true if we want to actually combine those two tuples and then output that to the result buffer. In terms of calculating the cost of nested loop joins, we are going to ignore the cost associated with writing out those resulting tuples back to the disk. Pretty much that's because of the fact that we probably have other operators in our query plan that we will be streaming those output tuples to. So therefore, we may not be writing those immediately to the disk. And also, for the different flavors of join algorithms that we will compare, the cost of writing them back to the disk is essentially the same because the output is basically of the same size. So how does this simple nested loop join algorithm work? As I said, we are going to basically load in each pages of R and S one at a time. So let's say, for the sake of argument, that our buffer pool can only contain 2 pages. So in this case, we're going to load in 1 page of R and 1 page of S. R has 4 tuples, and so is S. So we're going to first go through the first tuple of R, the purple one here, and then combine them with the 4 tuples of S, and then generate the appropriate tuples as necessary based on the outcome of passing those tuples into the theta function. So after we have gone through the first 4 orange tuples of S for that particular purple tuple of R, we're then going to load in the second page of S. Remember again, right? In this case, we only have 2 pages in our buffer pool available. So we're going to again take that one single purple tuple and then combine them with the second batch of orange tuples, right? Namely those in the second page. And then the same process goes on, right? So then we move on to the last page of S, and then we do the same process again by combining the first tuple of R against those in the third page of S. Now, we're done with the first tuple of R. We still have 3 other tuples in the page, right, of R that we have loaded in. So we're going to basically go down and then reload the first page of S again, but this time we're going to combine the second tuple of R against the first 4 tuples of S. So I think you get the idea here, right? So we're basically going to go and then iterate through every single page of S and then combining that with every single tuple of R. Until we're done with all possible pairings of tuples between R and S. So what is the cost associated with this particular flavor of the nested loop join? So assuming that these are the statistics of our 2 tables, and let's remind ourselves here that the square bracket here means the number of pages needed to store a relation, versus the bar basically represents the number of records. And then piece of R or piece of S represents the number of records per page. So the cost for this particular flavor of nested loop join is going to be the cost associated with scanning the relation R once, because we need to iterate through every single page of R. And then for every single tuple of R, we're going to combine that against every single tuple of S, right? So then the cost of the second term is going to be bar of R multiplied by the number of pages of S, otherwise known as square bracket of S. And then given the numbers that we have here for table statistics, we'll basically end up with 50 million as the final IO cost. Now, you might think about this in another way. So here we are going through every single tuple of R and then marching against every single tuple of S. But we don't have to necessarily go that way. We can instead go through every single tuple of S first, and then combine every single tuple of S against every single tuple of R instead. The effect is exactly the same in terms of the final output of the join, but then we'll see the IO costs actually differ. how does this work? So again, we have 2 pages available in the buffer pool. So we're going to load in 1 page of R and S just like before. But instead of taking the first tuple of R and then combining that with all the tuples of S, we're going to now take the first tuple of S, right, the orange one, and then comparing that with the first 4 tuples of R. Okay, and then after that is done, we're going to then load in the second page of R and then compare against the first tuple of S, and then so on and so forth until we are done with processing the first tuple of S. And then just like before, we need to reload the first page of R because now we are comparing that against the second tuple of S. And then likewise, the entire process basically keeps going until we are done with processing the first page of S, upon which we will then load in the second page of S and then do the same process again, so on and so forth. So all that we have done here is we have just changed the order of the join. It's still nested loop join, except that we're now iterating through every single tuple of S first. And then for every one of those tuples, we are going to compare that with the tuples of R. Otherwise, the loop body in this case is going to be exactly the same. Again, with the same statistics that we have, the cost of this particular flavor of the join is going to be slightly different. So instead of scanning R once, here we are scanning S once. And then for every single tuple in S, we need to scan the entire relation of R. So then in terms of cost, it's going to be square bracket of S because we need to scan S once. And then for every single tuple of S, we need to multiply that by the number of pages of R. So that's why we ended up in this case with 40 million as opposed to 50. So as we can see here, the ordering actually matters, right? So we can see that if we just switch the ordering, all of a sudden, we get much less cost in terms of I/O. And that is basically due to the nature of the statistics of the tables that we have in this case here. Now, the question is, can we actually improve even more in terms of cost? Turns out we can. So we look back at the picture here. So here we have processed 1 tuple of R against the first 4 tuple of S. Well, but notice that we actually still have the other 3 tuples of R that needs to be processed. So rather than marching down to the next page of S, why not take advantage of the fact that we have those the first pages of R and S already loaded into our buffer pool and use that fact to actually process the remaining 3 tuples of R against the first page of S instead of marching down the aisle. So what that means is we are going to, again, right, load in the first 2 pages, process the first tuple of R against the first 4 tuples of S. But instead of loading the second page of S after that, we're actually going to go and march down by taking the second tuple of R and then comparing that against the first 4 tuples of S, and then so on and so forth until we have processed the first page of tuples of R. So this is basically the idea of blocking, where we take 2 pages that are loaded into the buffer pool, and then we process all the tuples against each other first before moving on to the next page of one of these relations. So the same process is going to go on, right? So we're going to first process the first page of R against the first page of S. And then we're going to move down and then load in the second page of S, and then process that against the first page of R, so on and so forth. So now instead of processing 1 tuple at a time and then moving on to the next page, we're going to basically process all the tuples of the page that we have loaded in until we are done before moving on to the next page. So in terms of code, this is how we would express this page-based nested loop join algorithm. So for each page of R that we have loaded in, we're going to compare that with each page that we have loaded in terms of S. And then for each of the tuples that reside within that page of R and that page of S, we're going to once again pass that to the theta function that we have. Now, what is the cost associated with this flavor of the nested loop join algorithm? So here, again, we need to scan R once because we need to load in each page of R1 at a time. But instead of scanning S for every single tuple of R, we are now only going to scan S per page of R instead. So if we plug that into the formula, so instead of having bar of R multiplied by square bracket of S, we now have square bracket of R multiplied by the square bracket of S. So in terms of cost, if we plug in the numbers from before, then we basically get, in this case, 500,000 as opposed to 40 million that we had from before, which is awesome. The question is, can we improve this even more? Well, it turns out we can, but then it requires that we have more pages than 2 in our buffer pool. Okay, so instead of loading one page at a time of R and one page of S at a time, what if we can, let's say, load in 2 pages of R at a time? If our buffer pool in this case has capacity of 3 as opposed to 2, for instance, we can load in 2 pages of R against 1 page of S, and then do the same kind of processing where we process all the tuples of R against that same page of S before moving on. So pictorially, we will first, again, load in 2 pages of R, process all those tuples against the first page of S, and then after that, we load the next page of S, and then process all those first 8 tuples of R against the second page before moving down to the last page of S. And then after that is done, we will move on and then load in the next 2 pages, not 1, 2 pages of R, and then do the same kind of processing again by first iterating through the first page of S and then so on and so forth. This is the idea of block nested loop join. Well, so there's a limit, however, right? So our buffer pool is not of infinite size. So in this case here, we assume that we can have 3 pages. So therefore, we can load in 2 pages of R and then 1 page of S. What is the limit? If we have B pages total in the buffer pool, the maximum of pages that we can load in for R is going to be B minus 2, right? We need 1 page for S and 1 page for the output. So therefore, the maximum number of pages that we can load in at a time for R is going to be B minus 2. But against that, we are going to basically run the same algorithm. We're again going to load in every page of S and then find all the matching tuples, right, by calling our theta function. And then if it passes, then we're going to add the result to the buffer. So what is the cost associated with this block nested loop join algorithm? Again, we need to scan R once, right? Because we need to load in all these pages. Although here we're going to load in multiple pages of R at a time. And then for every batch or every block of pages that we load in to memory, we need to scan S against that. So therefore, the cost associated with that is going to be, again, the cost of scanning R once. So that is so that is square bracket of R, plus the number of pages that we have per block of R. And that number is going to be the total number of pages of R divided by how many pages we can load one at a time. And that is going to be B minus 2. And for every run of one of those blocks, we're going to scan the number of pages that we have for S. So that's why it's get multiplied by square bracket of S. And then if we plug in the numbers here, then we finally get around 6,000, assuming that we have the buffer pool size of 102, which is way, way better than our previous version of the page nested loop algorithm. This turns out to be a fairly commonly used join algorithm, so that's why we covered this in this class. Although, as I said, it has the requirement that we need to have enough pages in the buffer pool in order to accommodate for this block-based operation. Obviously, in the limits, if we have enough buffer pages to load in all of the relation of R or S, then our costs will be even simpler, because then we basically just need to load in once, and then we don't have to do this repetitive process of going back and forth. But then, of course, for practical relations, we pretty much know that that is not the case, as we have seen earlier in our lecture.